Okay, so we have the problem of 2 points, think of 2 points in R2. And we can think of R2 as a vector space V if we want to. Okay. And they're going to be fit by this straight line, y equals b plus ax. Now, first thing I ask is write the system of simultaneous equations that you would solve for A and B. Okay, well, that's very straightforward, but of course, yeah, there's a little confusion. Some people, I think, may be thinking this is the backward apostrophe B thing and the backward apostrophe A. Now, that makes it a little difficult to get started, but there's no backward apostrophes. So those are just parameters. Those are the variables that you're going to solve for. And once you've solved for those variables, then you have a straight line, the equation of a straight line through the points. Okay, well, just taking, let's say the points are 5, 9, and 11, 15. Everybody's got different points. We've got y equals b plus ax. We want y equals b plus ax. So we can just substitute when y is 9, x is 5, or when x is 5, y is 9, right? So we put 5 in for x, we get 5a. B stays b, and y is going to be 9. And same thing here. X is 11, y is 15. So if x is 11, we're going to get 11a, and we're going to get 15. Notice we always have b. Okay, that's going to show up in your matrix. Okay, so now we want to write this as a matrix equation. Okay, well, the matrix equation is simply, I'm just going to write this down without a whole lot of explanation, but it's, well, we're multiplying some matrix by we're going to do B and A for reasons. That doesn't have to be this way. It's just going to be easier to see how the matrix reduces and stuff like that if we have B first, because B always has a coefficient of 1. And we'll see how that works. And then this should equal here, right hand side, which is 9, 15. Of course, those are your y values. So what's the matrix? Well, the matrix, you're multiplying b by 1 and a by 5. And the first, you get the first equation, so you get 1, 5. And you multiply it by, you get 1 and 11 in the second equation. You got 1, 11. Well, this gives you b plus 5a equals 9. And b plus 11a equals 15, which is your 2 equations. So of course we need to be real clear on how we translate an equation into a matrix, because everything starts with systems of simultaneous equations. Now, stupid camera, it's been stable ever since I turned it on 10 minutes ago, but it just zoomed back. So you're seeing way too much of me and way too little of the board. Yeah, board looks much better. Okay, so here we have the system of equations. And I think it was visible. I don't know what to do about this camera. Other than that, it worked great. Okay. So here's our system of equations. Okay. Now, question is, what's the rank of the matrix? What's the basis for the column space? Okay. To put these questions in context, we can think of this matrix as a transformation from R2 to R2. Okay, I didn't say to do that, but I'm going to do it. Okay. I'm going to think of this as representing transformation T from to W. Okay. Where P and W are both two-dimensional real spaces. Okay. So we can even kind of draw this. Here's V. Here's W. And I'll just write a matrix. Actually, we call that the transformation T. We're going to think of the matrix as representing the transformation. Okay. So now we're into the context of linear transformations. We don't need to have that context to do the rank in the column. The rank and the basis for the column space, we're going to do it anyway. Okay, so the rank of A, well, it's 1, 5, not 1, 15, 1, 11, reduces to 1506, which then reduces to the identity. So we have two linearly independent rows. So the rank is 2. Okay. Similarly, column space has dimension 2 because that column space has the same dimension as the row space. And it's clear that from either this form or this form that the first column and the second column span. Okay. Now that's the first column and the second column of the original matrix, not the first column and second column of the reduced matrix. Okay. When we reduce the matrix, remember, we're adding multiples of rows and to rows and multiplying rows by numbers, none of which changes the span of the two row vectors. Okay. However, it does change the span of the two column vectors. It doesn't change the dependence of the column vectors. Okay. So these two vectors are linearly independent. These two columns are linearly independent. And the column space is then spanned by these two vectors. Okay. So what we have over here is the row space, which is the whole thing. And over here, this is an R2, it's spanned by two linearly independent vectors. So column space is the whole thing over here too, right? Okay. So V is the row space. W is the column space. Fair enough? Okay. Well, I'm going to go a little further with this. Clearly, if you have 2 points in the plane, you can draw a straight line through those 2 points. Okay. If you got 3 points in the plane, maybe you can draw a straight line through them. But if I gave you the 3 points, okay, well, consider. Okay. Consider these points. It's very unlikely that those 3 points lie in a straight line. By coincidence, it could happen, but probably not. Okay, so we get 3 points. That are connected by a straight line. Okay, we want to find the straight line that best fits these 3 points. Well, let's just say that my 3 points are four, 5, nine, 6, and 12, and 6, 10. Okay, just take 3 points that are clearly not in a straight line. And we can see they're not in a straight line. The slope from here to here is much different than the slope from here to here, and that's enough to show that they don't lie in a straight line. Okay. Now, there is a straight line that fits these 3 points better than any other. Okay, so maybe the straight line is this. Okay. And maybe the y-intercept is 0, 1. And maybe the slope, well, let's see, if this is at y coordinate 10, 12, y coordinate here might be 10. So from here over to here, you got to move. Now the y coordinate here is 10. I'm not dyslexic, but sometimes I'm really dumb. Okay. And there's a big difference between dyslexic and dumb. I think I mentioned my graduate school advisor had written a major paper, got tenure at a really selective institution, and I worked with him for 2 years. He was dyslexic and I never knew it. Okay. So anyhow, so he's smart as heck, and highly accomplished. Okay, well, anyhow. So anyhow, the coordinate here is 10, so I'm going to estimate that the coordinate here is, it's not very well drawn to scale. I'm going to pretend the coordinate here is 9. And then the run from here over to here is 12. So the slope is going to be 8. The rise from here to here is going to be 8. The run is 12. So the slope is 2/3. Okay. So equation y equals 2/3 x plus 1. Okay. Now that's almost certainly not the best fit equation. But from this equation, you would then ask, if you take this distance, which you can easily calculate, if x is 4, you plug in 4, 2/3 of 4 is 8/3, and 1 is 3/3, so that's 11/3, right? So the coordinate of this point would be 11/3. It's on the line. Okay. Your deviation of this point from the line is, I'll color code this. Okay, your deviation is 5 minus 11/3. Which is 4/3. Okay, 1 1/3. Here's your deviation. there's a deviation here. And a deviation here. Get the deviation for each point, you just find the, okay, if x is 6, if x is 9, 2/3 x is 6, 1 is 7, right? So the y coordinate here is 7. Y coordinate here is 6. Deviation 1. Okay. Over here, the x coordinate is 12, 2/3 of that's 8. You add 1, you get 9. And the deviation here, the y coordinate is 10, right? Y coordinate here is 9, y coordinate here is 10, your deviation 1. Okay. 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 Square 4/3, you get 16/9. Okay. And then 9/9 and 9/9, 34/9. Okay, that's not bad. The best fit line minimizes the square deviation. Something you should probably keep in mind forever. Okay. Now you can minimize the square deviation by writing an expression in terms of A and B for the deviation, square deviation, and using calculus to minimize it. Not difficult. Okay. What we're going to do with linear algebra does the same thing. And you're at a point in calculus where you totally can understand that optimization. Okay. You don't even need integration. So you could have done that, months ago. And I almost always teach this in an applied calculus course. Usually not in a engineering calculus course, just because of time and priorities. But it's a fairly easy exercise. Okay. Now, it turns out it's fairly easy here, but it's more complicated in terms of subspaces and so forth. So let's see what happens with linear algebra. So this is our goal, is to find the straight line that minimizes this. I'm thinking this line isn't too bad for those points, but hand sketch graph, ballpark estimates, it's not going to be right. Okay, so what we have now, well, can you do what we just did? And I'll put this back up so you can see it for this situation. Now you've got 3 points, you're going to have 3 equations. And your matrix is not going to be square anymore. So basically all I said was, go ahead and do what we did here, but for these 3 points, and see how things change. Okay, I'll dispose of that very quickly. And you could have done it, you probably did it for my numbers, but maybe you did it for your numbers, doesn't matter. It's going to be the same, it's going to look the same either way. Okay, so you get it, for the first point, if the first point is 4, 5, you got 5 equals B plus 4A. Here you would get 6 equals B plus 9A. And here you would get 10 equals B plus 12A, if I've got all that. Okay, and that leads you immediately to the matrix 1, 1, 1, 4, 9, 12, multiplied by B, A. And the reason I've used the order B and A, because usually when you write the equation in a straight line, you'll take mx plus b form, right? But it's simpler if the ones are here because it's really easy to reduce the matrix. Okay, because you immediately wipe out all of this column except for the first. Then things can get a little more complicated. But there we have the matrix, and that equals column 5, 6, 10. Okay. Now we can reduce the matrix. Okay, so made that matrix a little too narrow. So a little separation there. It's not 14, 19, 112. Okay, it kind of looks that way. Okay, this reduces to ultimately 1, 0, 0, 1, 0, 0. Okay, so the rank is 2. And a basis for the column space would then just be these 2 columns, because again, the first column and the second column have leading ones and so forth, so that the first column and second column of the original matrix form a basis for the column space. Okay, they span the column space and they're linearly independent. Okay, well, that then would be consists of vectors 1, 1, 1, 10, 4, 9, 12. Okay. Now, previously, the picture of the V and W spaces was not very interesting. Okay, because your rows span V and your columns span W, and it was just R2 and R2. Okay, so could be a little bit of interest there, but not particularly. But this gets more interesting because we're going to talk about this for a minute. But the question is, what's the space V and what's the space W? Okay, so again, my question is, if you got V and W and A as a transformation, what's the dimension of V and what's the dimension of W? Well, V consists of the vectors that you're mapping. The vectors you're mapping are BA, are BA vectors. Those vectors have dimension 2. That means these are vectors in R2. Okay. The vectors that you get are in W, which has dimension 3, because you have 3 components. Okay. So V is an R2, and W is an R3, is an R3, right? What's the dimension of the column space? Well, it's got a basis consisting of 2 linearly dependent vectors. It's dimensions 2, so it's a subspace of R3. Okay, so your column space You've got all this stuff out here that's not in your column space. Okay. We can even draw a picture of this. Here we have R2. Okay. With basis vectors, well, we might as well take the simplest possible basis vectors, 0, 1, 0, and 0, 1, right? Expressing the vectors as columns, but the rows are the vectors, so you know, take a little liberty there, not really. Okay, there's R2. Now how are we going to draw R3? Okay, here's R3. We'll call this X, Y, Z. So this is our first coordinate, second coordinate, third coordinate. What's the basis for our column space look like? Well, it's got 1, 1, 1, right? And it's got 4, 9, 12. Now I could make this 0.4, 0.9, 1.2 if I wanted to. You know, I could shorten that vector. I'd still have a basis. We don't have to use these vectors for the basis, but we'll go ahead and do it anyway. Okay, so 1, 1, 1. Okay, well, here's, let's say where X equals 1, here's where Y equals 1, here's where Z equals 1. And well, here's the 0.11 down in the XY plane. And we move up 3 units. It's pretty inconvenient. I'm going to redraw this. Probably should have thought it through. I just want to redraw it to kind of rotate it a little bit more. And I'm going to stick with it. Okay. So you just draw a box. I don't know if you can really see that, but that's like a 1 by 1 by 1 rectangle, right? And the vector 1, 1, 1 goes from the origin out to here. So here's a vector. Keep the notation consistent. I'm going to write it as a so vector 1, 1, 1 is in here. You can't even hardly see it because you're almost looking at it end on. Okay. But here's the line. Of 1, 1, 1. Okay. And that's actually a subspace of the three-dimensional space. In other words, the set of multiples of 1, 1, 1 is a subspace. Very simple subspace. You can represent it geometrically as this line. And then we have 4, 9, 12. Okay, well, that's going to be a little easier to draw. 4 is like out here. 9 is out here. 12 is way up here. Okay. So 4, 9, 12. If we draw a rectangular box, this vector is going to be like so. Okay. And it's got a different line. Okay, so here's at least a depiction of the vector 4, 9, 12. And here's the line. that vector. Okay. Now, these two vectors span a plane, the set of all sums of all multiples of this vector and this vector, which means every vector you can get by taking a vector from the origin to a point on this line, added any vector you want from the origin to a point on this line, forms a plane. So you got this plane in R2, and R3, I'm sorry. The plane is a subspace of R3, and could have drawn this better. Okay, so you got some plane there. This is the plane spanned by set 1, 1, 1, 4, 9, 12. Okay. And there's another name for that. Somebody want to give me another name for that? What do we mean? So somebody told me that's almost unreadable. Not writing very well today, but that's the column space. So you can visualize the column space in this situation as a two-dimensional subspace of R3 with some orientation. Now the orientation, you know, if X is here, Y is here, and Z is here, 1, 1, 1's kind of at equal angles with all the coordinate planes, the X, Y, the Y, and so forth. So it's good. It's like that. Okay. 4, 9, 12, we come out here 4. Then you go over 9, which is further. So already you're in this direction. And then you go up 12. So you have a vector like this and a vector like this, and they form a plane. Just lay a sheet of glass over those two vectors. There's only one way to do it. And there's your plane. Okay. So your plane's kind of here. Doesn't really matter where it is, but let's now think about where this vector is. Is this vector in that plane? Probably not. If it is, changing one number would make it not, but probably not, almost certainly not. If it was in that plane, then you'd have a straight line through all 3 points. Okay, now that's a connection, you know, you have to think a little bit to make, and I'm not going to push it at this point, but the big point here now, and this is as far as I'm going to go with this model, because I want to talk about complex variables, complex numbers. Okay, get you started on that. The vector 5, 6, 10, we come out here 5 over 6 up 10. It's not far from this plane, but it's not in this plane. Okay, so the vector, this is our target vector. We can't hit it unless the 3 points are on a straight line. Okay. Our target vector is out here someplace, not in the plane. Okay, let's just say that's it. 5, 6, 10. That's not probably where it would really look like it is, but it figures. kind of messed up. Okay. It's not in the plane. Okay. What vector in the plane is closest to this vector? Well, it's the projection of this vector into the plane. And we learned some time ago how to project a vector on a line or on a plane. Okay. You just project the vector on each of the basis vectors that take the sum. Okay. And you get, well, we'll deal with that. But the thing I want you to take away now is this vector projects into the plane. So I'm going to have a vector like here. Okay. And what I'm depicting here is the right angle projection of this vector into this plane. Okay. So this vector is projected into the plane. Should have a place to write this. And right there's the projection. Okay. The vector over here in V that this came from gives you as components of A and B and A, which are the parameters you need for the best fit straight line. Okay. Now I'm not going to write that down at this point. If you have this much of the picture and review this a little bit, then when I talk about the rest of it, it'll be clear. Okay. You have your four basic subspaces. In other words, over here, you have the row space and the null space. Okay. Over here, you have the column space and the null space of the transpose vector. Okay. Transpose matrix. Those are orthogonal subspaces, and we put all those ideas together to understand the process. This is the first part of the process. We've got this vector here. We've got the column space. It's easy to get those. And then we can project this vector into the column space. And then we figure out where they came from over here. That's the process. And it's easy to visualize in R2 and R3, especially if you draw better planes than I did. Okay. I could have chosen my vectors a little better. I could have used smaller numbers here, so the length of this vector and this vector would be closer together, but I didn't. Okay,